So the story of standing waves is the story of interference of the wave with its own reflection. So just a quick reminder of what interference looks like. Here's the story, for example, of destructive interference, where I have two waves that are occupying the same space at the same time. In this case, it's just pulses, two pulses, but are occupying the same space at the same time. And their amplitudes add, but because their amplitudes are in opposite directions of each other, then they end up destructively interfering, and then they pass each other like this. This is called destructive interference. On the other hand, if the two pulses have amplitudes that are in the same direction, then when they happen to interfere, they interfere such that the amplitude adds up, and this is called constructive interference, where I get double the amplitude, and then they pass each other again. So this is the phenomenon of constructive interference. Now, the phenomenon of standing wave, which we're talking about today, is the phenomena of the interference of a wave with its own self. So to understand that, or with its reflected self, to understand that, we first need to think about the reflection of the wave. So to do that, I have to think about there's different kinds of reflection depending on whether you're reflecting off of an end that is fixed or an end that is loose. And you'll see the difference in a second. So suppose, for example, that I make this end fixed, meaning that this green ball is never going to move from its spot. So that means if there is a pulse that is coming in and is going to try to pull, so the red ball that is right next to it is going to try to pull the green ball up, but because the green ball is fixed, then it's going to exert a force opposite direction to the red ball, and we'll see what happens in that case. So suppose I just get a pulse going, and then by the time it reaches this ball here, it's going to try to pull the green ball up, but because the green ball can't move, then the pulse is going to be reflected and inverted because it's off of a fixed end. Now this end also simulates a fixed end, so you'll see that it again is going to reflect, and when it reflects, it's going to invert. On the other hand, if this is a loose end, that means the green ball can move if it wants to. So when the pulse gets there, it's going to pull the green ball up, and now when it reflects, it actually reflects without inversion. So here it's going to reflect with inversion, and then when it gets to a loose end, it reflects without inversion. You see it here again. Reflection without inversion. So depending on this end, whether it's a fixed end or a loose end, you either get reflection with inversion or without inversion. If I send in, instead of just a single pulse, I actually send in a periodic oscillating wave at a specific frequency, you'll see that what happens, I'm trying to simulate a fixed end by just making this not move a lot. So you'll see what happens now when I send in an oscillating wave and it interferes with its own reflection. It gives me something that is known, a phenomenon that is known as a standing wave. So here the energy keeps building up into the pulse, and I keep getting this string oscillating at that specific frequency, such that it looks like the wave is just standing on that. So it just keeps going back and forth between these two extremes of position, right? And that's a specific frequency. And I'll prove it to you. Suppose we change the frequency. If you notice down here, right now I have it at 1.5 hertz. And I get this really nice periodic wave that keeps going back and forth between the two extreme positions. Suppose I change this frequency to something like 1.25 instead of 1.5. Let's see what happens. Now you'll see that it's not really a very nice, it's kind of close to a standing wave. It's not exactly a standing wave. Actually, it's a nice standing wave too. Yeah, this is a nice standing wave too, but it's just less. Right, because I can see these red balls right here. This one is standing still, this one is standing still, this one is standing still. So these are all, this is also a standing wave. I mean, you can see it's a little bit off, right? Because I get these things that are these shapes. But if I put this at some number, some different number here, let's say, and I start again. Now, this is definitely not a standing wave. I mean, at some point, this looks like it's standing, but then now it's moving, right? And it just keeps reflecting, maybe destructively interfere, and then it's not building up, the energy is not building up like it was when I was thinking about a standing wave. So the standing wave pattern only happens for specific frequencies. And to find out these frequencies, let's think about them in this picture here. These are called the standing wave patterns. These points that are not moving at all, we call them nodes. So in the first pattern here, this would be called a node here and a node here. So I just have two nodes. In this pattern, I would only have these nodes here, 1, 2, 3. Right? So the points that are not moving, they're called nodes. And here I would have 1, 2, 3, 4. Now the points that move, the maximum position here, the maximum dispersion, these are called the very clever name antinode. So an antinode is the place where it actually oscillates the maximum oscillate. So of course the pictures that you're seeing here are pictures over time of this thing fluctuating back and forth between the same positions. But because we're showing them all at the same time, then you see sort of the overall envelope. But this one here for part B, for example, you get the string going like this, and then it goes back to this position, and then it goes all the way to the other extreme position like that. Yeah, so it oscillates back and forth between these two extreme positions. Okay, this here is called the first harmonic, the fundamental frequency, and the reason is that you can't get any less than that. If you want two nodes, so in any wave like that, if I want to have 2 points, the nearest 2 points to each other such that I get no nodes in between, this is the best you can do. So this is the smallest frequency because it's the biggest wavelength. Remember, on a string, once you fix the tension and you fix the mass per unit length, then that means you're fixing the speed. So the speed here is fixed, right? Speed on the string is fixed because I fixed the tension and I fixed the mass because I did not change the string at all. So once the speed is fixed, if I increase the frequency, the wavelength decreases and vice versa. So the minimum frequency would be for the longest wavelength. The longest wavelength happens when I get these two nodes here. Suppose I have a string of length L that is fixed at both sides under some tension F, and it has a mass M, and I want to find out what frequencies would actually produce standing waves on that string that is fixed at both ends like this. It has a length L, and it has mass M, and it's put under tension F. In other words, because I know the mass and I know the length and I know the tension F, then I also know the speed of the wave, right? Because if you remember, the speed of the wave on a string that is under some tension F is equal to the square root of the force of tension divided by the mass per unit length. So that means that I also know the speed. Yeah. And what I'm looking for is, I'm looking for the frequencies that would produce these patterns, the standing wave patterns. The first standing wave pattern is the one that we call the fundamental frequency, and it looks something like this. If this is the equilibrium position, then a standing wave of fundamental frequency is going to oscillate between this location and this, or between this pattern and this pattern. The whole string is going to oscillate back and forth like that. So that means that I know what the wavelength of this wave is. If I draw it like this as sort of an extension, then this would be a full wave. So that means that the length of the string here is half the wavelength of the fundamental frequency. So that means that the wavelength is equal to twice L, as you can see. If the length of the string is L, then the wavelength of the fundamental frequency is twice that. I'm not looking for the wavelength though, I'm looking for the frequency. I know that the frequency and the wavelength are related by the fact that the speed of the wave is equal to the frequency times the wavelength. So I can always say then that the frequency would be the speed divided by the wavelength. So the frequency then would be equal to the speed of the wave divided by the wavelength, which in this case is twice L. And you know how to calculate the speed because you know the tension and the mass, so you can always calculate the speed and put it right in there. Or maybe you already know what the speed is. Like let's say it's a known phenomenon, so you know the speed of the wave or you know the speed of the wave. Anyways, this is called the fundamental frequency. It's sometimes called F sub 1 for fundamental, the first harmonic. Now, suppose I want to think about the next one, the next standing wave. What would it look like? If it's fixed on this side, then it has to be a node. Fixed on this side has to be a node. And this is what we saw here too, a node and a node. And we got one antinode in the middle. But I could also get a node in the middle here, right? And that would mean that I would get a pattern, standing wave pattern that looks like this. This is one extreme. I'm exaggerating really the whole thing, right? So you can see it. So this is one extreme and this is another extreme like this. So it keeps oscillating back and forth between these two. And in this case, the length would be equal to the wavelength. It's a full wavelength on this length here. So that means that the frequency then would look something like this. The speed divided by the wavelength, but the wavelength is the full length. So in this case, the frequency would be the speed divided by the length. What about the next one? What I have is I have a node on one side, a node on the other side. I have to, because if it's fixed, there has to be a node there. And then instead of having one node in the middle, I can have two nodes in the middle. So that means it would look something like this. This would be the standing wave path. So it goes between this extreme and this extreme like that. And in this case, you can argue that the length of the string contains 1.5 wavelength. Wavelength from here to here, right, a full cycle, and then another half. Which means then that the wavelength would be 2/3 of the length. Which means that the frequency then would be the speed divided by that wavelength, so it would be 3/2, and so on. What about the next one, and the next one, and the next one? Let's try to come up with a general pattern. Let's try to come up with a pattern that says the nth harmonic looks like this. Can you see a pattern here? Obviously, it looks like there is always a speed divided by the length of the string. And then I get, suppose I write it like this. Maybe you'll see the pattern a little bit clearer if I write it like this. 1/2, 2/2, 3/2, 4/2, etc. So this would be n/2. Should be n/2 of the speed divided by the length, where n could take any value, 1, 2, 3, any integer value n. If n is 1, then I recover this, the fundamental frequency. If n is 2, then I recover this one, second harmonic. If n is 3, then I recover this one, and so on. So this is what we get. The first harmonic, that's called the fundamental frequency. The second harmonic looks like this. The third harmonic, and so on. Notice that the relationship of the frequencies is that frequency, the fundamental frequency is f1. The frequency of the second harmonic is twice the frequency of the first harmonic. That's because I go from 1/2, the speed divided by the length, to 2/2 to 3/2, so I get 3 times, 4 times the frequency, and so on. So that's the transverse standing wave pattern. If the string is fixed at both ends, then I can always write the nth harmonic frequency as n times of the speed divided by twice the length, which is the fundamental frequency. You can see that the frequency really depends on a couple of things. It depends on the speed, the frequency of the standing wave depends on the speed of the wave, which depends on the tension and the mass per unit length. And it also depends on the length between the two fixed ends. So for example, you can look at a guitar like this and you say the length between the two fixed ends typically is between where this knob is, right? That's where it's tied, where the string is tied, and this like fret on the other side. So then this would be the length. So the tension on the guitar string then would change the speed of the wave on it. So that's one way you can change these frequencies. You could also change the guitar string itself so that would change the mass of the guitar string, by therefore changing the speed of it. Or you could also move your finger. And when you move your finger and you press down here, you effectively shorten that length. So you can get different frequencies by pressing your finger at different spots. So if we go back to the simulation that we had at the very beginning, and we're looking here at medium tension, so that fixes the speed for me because I can't really change the mass of the spring. So I'm changing the speed of the wave by changing the tension here. I put it on medium tension, and then the length of the string is fixed. You can put the ruler here and measure exactly what the length of the string is. And then I put a particular frequency here, and I've simulated having two fixed ends by having an actual fixed end on this side with this clamp. And on this side, I'm making the amplitude so small that this is really not moving at all, almost. But I need to have a little bit of amplitude just to put some energy into the thing. And you see here a standing wave. And if I pause it here at some point, we can count how many nodes we have. So I have the green balls here. I've fixed it such that I got the green balls to be the nodes. This is a node because it's right on the equilibrium position. It's not changing as you play this. See, the green balls are not moving at all. So the green balls here, they're indicating the nodes. So I'm going to get 1, 2, 3, 4, 5, 6, 7 nodes. And in between the nodes, I get one antinode, 2, 3, 4, 5, 6. So this is the sixth harmonic, because the first harmonic has only one antinode, the second harmonic has two antinodes, and so on. So this would be the sixth harmonic. So if the sixth harmonic is at 1.5 hertz frequency, then I would imagine the fundamental frequency would be something like a quarter of a hertz, right? So let's test that assumption here. Either exactly a quarter or like a little bit, maybe we're tiny little bit off, but let's see. If I put a quarter of a hertz frequency in here, let's see if I put some energy. We're going to have to wait a little bit to see the energy build up in here. And let's see if this will give me the fundamental frequency of this string. Fundamental frequency would mean that the two ends are fixed and I have an antinode right in the middle, and the string is oscillating back and forth, which looks like exactly what we're getting in this story. Now, obviously, if I change the tension, then this is no longer the same frequency will give me the fundamental frequency, obviously, because when you change the tension, you change the speed, and changing the speed for the same length will give you a different harmonic frequency. Okay? Now, suppose I have, instead of a fixed end on this one side, on both sides, I have on one side a fixed end, and on the other side, I'm going to turn it into a loose end. Now, in this case, obviously, I'm not going to have the same kind of response because when this reflects now, it reflects in a different way. So how do I figure out standing waves in this case with one side that is loose end and one side that is fixed end? That's the next story that we're going to do. So again, the setup is similar. I have a string of length L, but this time I have a loose end on one side. And a loose end means that on this end, I have to have an antinode instead of a node, right? So I'm going to have a node here and an antinode here. So if I look at a wave like this and I say, what's the smallest distance between a node and an antinode? This would be a node, this would be a node, dot, dot, dot. and this would be an antinode. So the smallest distance would be a quarter of a wavelength. So in this case, the fundamental frequency would happen when the length of the string is equal to a quarter of a wavelength, which means that the wavelength would be 4 times L, which means that the fundamental frequency would happen when this exactly at the speed of the wave divided by 4 times L. So this is called the fundamental frequency in the case that I have a fixed side and a loose side, right? So this would look something like this. Okay, it will oscillate back and forth between these two extremes like that. Now suppose I look at the next part. Well, I need a fixed end and I need an antinode on the other side. So the smallest would be this here. It would look something like this. It would look something like half a wavelength and then a quarter of a wavelength like that. It will oscillate between these two positions, right? So that means that the total length then would be 3/4 of a wavelength, which means that the wavelength then would be 4/3 of a length, which means that the frequency would be the speed of the wave times 3/4L. What does the next one look like? Maybe pause the video and see if you can do it yourself. If I want the next one, that means I want to go from a node here, and then this is the first antinode, this is the second antinode, and then I want it to go to here. So that's a wavelength and a quarter. And so it looks something like this. Whole wavelength and a quarter. Like that. So I say it's a whole wavelength and a quarter, so 5/4, which means that the wavelength itself is 4/5 of the length, which means that the frequency is 5/4 of the speed. This should say wave, speed of the wave divided by the length. Can you see a pattern here? 1/4, 3/4, 5/4, etc. So yeah, the pattern is the following: that the would have an n times the speed over 4 times the length, but n this time can only take the odd integer value. There's another way of writing this that you might find out there, but I like this way of writing it, so it's easy to remember, because now I'm thinking about quarters, but I'm only thinking about odd quarters: 1/4, 3/4, 5/4, and so on of the way. So let's see how that would look like on the simulation. So suppose I simulate a fixed end on this side by making the amplitude really small, and a loose end on this side by picking the loose end here. And then I'm going to pick a frequency here. I would have liked to write 1.375, but 1.38 is close enough to what I want. And let's see if I start putting some energy into the system here by oscillating at exactly this frequency. And remember, this is at medium tension here. So let's see if I get a standing wave pattern here. You can see that it's starting to develop, right? You can start to identify which parts are really nodes and which parts are antinodes. This bulb, for example, looks like it's not moving much, so it's a node. Here's another one that is not moving, so that's a node. Right? All of the bulbs that are not moving as this thing is oscillating, that's a node, that's a node. Maybe I'll pause it at some position, and then you can see the extreme position here. These 1, 2, 3, 4, 5, 6 nodes here, right? I have 1 antinode, 2, 3, 4, 5, 6 antinodes, because this is obviously fixed and loose on the other end. And then you can say, you know, here's a full wavelength, 2 full wavelengths, and 3/4. So 2 and 3/4. So that's 1/4, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 quarters of the wavelength. So my first harmonic is 1/4, 3/4, 5/4, 7/4, 9/4, 11/4. So this is my 6th harmonic for fixed and loop.